besides myself and Wei Han, there's a bunch of people that have contributed into UFO, QCs and Obs function and things like that. So this is a very short list. The list would be extremely long if I put everybody on here, but Ryan and Emily and Wojciech at the Met Office and a whole bunch of other people contribute into this work. So I want to recognize them. Okay, I have to use a different button. Okay, so the outline of the talk is here. We're going to go over some QC configurations that some are simple and some are more complex for screening the data. Then the OBS functions, we're not going to obviously go through every one of them, but I'll give you a flavor of some of those. We'll start out with conventional data. This does sort of follow the practical that we just had yesterday with the satellite winds example and the quality control of satellite winds. Then we'll switch over to Wei Han to take over for the satellite radiance work, and he'll go over bias correction. He'll show you some better plots today that go along with what was seen in the exercise yesterday. And he'll wrap it up with the satellite radiance quality control. So bias correction first, quality control second in the radiance data. Also, Fabio gave a very nice sort of general overview of a lot of the capabilities here. So I'm going to spend a little bit more time on individual components, more so than Fabio did. But here is the list of really the simple and generic filters that are very commonly used. We have a bounds check. So I have a little text explanation to the right of each one that sort of says what's going on with it. Is a variable within a physically sensible range? Domain check, is the observation near the poles less accurate? These are just examples. Obviously, domain check could be near the tropics or near the poles. It's just generic for windowing away regions that you might want to eliminate as your data. Background checks, is the observation drastically different than the model background, O minus B essentially. We used to have and we still do, have a filter called blacklist. Some months ago, those were changed by Wojciech at the Met Office to reject list and accept the list. This is a nice little addition because in a sense, blacklist, besides the stereotype name that we would like to avoid, also was used in some weird ways. Like you would use a filter called blacklist, but you would run a step that was assigning observational error, which was a little odd, but this has been cleaned up quite a bit with these, I think, better filter names of reject list and accept list, and they do exactly what they say. You are either rejecting some observations because of some condition, or you are accepting some observations because of some condition. And the classic example of that is you can think of a way to just reject all surface data from some mesonet where you don't trust the quality. And maybe you'd want to accept list of a certain data set that you expect to be really high quality. And you could always later reject some of its observations with like a background check, if that was necessary. A difference check is very nice. You can use it for just about any two variables you want. They could be two brightness temperatures of two different channels. That's done very often in our field. Subtracting a shortwave radiation and a long wave radiation tells you something different about the clouds. But you could subtract air temperature. Well, really the sky's the limit there. Model ob threshold is interesting because it's similar to background check, but it does have some differences that you can put in a vertical. So you might want to reject relative humidities of drastically different values near the surface and might do less of that. You might change that background check threshold higher up in the atmosphere. So you have some options to not make it just a global one value everywhere difference check or background check. There are usually actions associated with some of these. The default action is reject, but there are some other actions that you can choose in there. And I'm pretty sure that every one of these takes the where clause, and the where clause is extremely powerful to target some exact type of observation or to target some very physical bounds. Some temperatures above 300 Kelvin could just be a where clause all by itself. So the flexibility here is really nice of these where clauses. And you can say where clauses that include multiple variables. So you can, and they're all anded together, binary or logical and. So where temperature is greater than 300 and where humidity is less than 10%, something like that example. Some more complex filters include thinning filters. There's a regular thinning filter, Gaussian, temporal thinning, and Poisson disk filtering or thinning. These are all, I think, contributed by the Met Office, if I recall correctly. There are derivative checks. That's just any dx dy, which is really nice because that could be depressure, dtime, or it could be detemperature, dx. I forgot why I put x in that position, or dz. That was meant to be a z, a z. So a lapse rate, for example, a derivative check is a lapse rate. That's quite helpful. Nice and still generic, but certainly more complex than a background check or a bounds check. There's a track check, which is the airplane flying too fast, is the boat moving in a weird direction or too quickly or whatever. There's a Met Office buddy check, and the Met Office included a lot of vertical profile checks, and those are very nice for radiosondes or other vertical profile information. There are also a series of some variable transformations. These have just begun, but I envision there'll be a lot more of these. So I think I've discussed this briefly yesterday, that the UFO variable internally for the model information is generally specific humidity, but we may want to assign the observational error done with relative humidity. So there's going to always be times where we need to transform variables. The wind variables are the same, it's U and V wind components, but we often need to have wind speed and direction for various other filtering steps. So this is the variable transforms library will grow for sure. And by the way, the humidity calculators for specific humidity, dew point, water vapor mixing ratio, all of these things actually have multiple methods internally because there are different assignments of the saturation mixing ratio by different centers. I contributed one, Met Office has one, there's a long-standing one used at NCEP for calculating like relative humidity. So there's actually multiple methods in some cases to do variable transforms where you can even pick the method within the transform. Rather importantly, rather than that blacklist filter or bounds check or other named filters, there's now a very highly specialized filter name of perform action, because some of these filters are not really filtering data. They are performing actions. They're assigning observational error. They're inflating observational error. So typically used with simple methods for like a lot of these steps, but you can also do much more complex things using these OBS functions. And we didn't spend any great time on that in any of the talks yesterday by Ryan or Fabio mentioned them. So I have an example one where the assignment of the OBS error might be height or pressure dependent. I'm going to show a plot of that, or perform different functions in cloudy versus clear sky regions, for example, in satellite radiance data. So what are OBS functions? A little bit more about OBS functions is they are generally designed when generic filters can't fully achieve a goal. We sometimes need a specialized code in an OBS function to handle the more complex tasks. That was mentioned yesterday, I think, by Wei or Fabio. The hydrometeor check would be different maybe for AMSUA than ATMS, than SSMIMS, and so forth. Cloud liquid water check in the microwave region, surface Jacobian. These are just some of the examples. In conventional data, there's surface pressure error inflation that really is unique. You really can't write such a generic filter for that. And I think I have the graphical example of this model stepwise linear for the assignment of the OBS error. And satellite winds examples of some very specific OBS functions are a wind direction angle difference. So just because we have a U and V from satellite AMVs, atmospheric motion vectors, we may need to check that the winds aren't so orthogonal that they'll give us a problem in the DA system, solving that so we can reject winds of a direction difference of some threshold. And tropopause estimate was in that filter from yesterday's practical as well, where maybe we just want to reject anything that looks like it's in the stratosphere above the tropopause because of being unreliable, since we shouldn't expect clouds and therefore atmospheric motion vectors to occur at extremely high altitude. I think I have an example of how this stepwise linear works. Yep. This is the YAML that goes with such a thing. So the filter is perform action instead of bounds check or something else. And we're going to do the action of assign the error. So the initial assignment of the error follows this vector at the bottom, where the X vals are the pressure wherever the observation is, whether it's near the surface or aloft. And the second vector at the bottom line here is the actual assignment. And in between each of these values is linearly interpolated. So between 100 millibars and 200 millibars, we want to ramp the assigned absolute or OBS error from 3 Kelvin to 2 Kelvin. And up here is the filter variable. Sorry, I forgot to mention air temperature is what we're going to be working on here for this assignment of error. So the errors is listed as basically an air temperature in Kelvin or Celsius in this case. And you can basically even have it ramping up and down. So the graphic on the right shows that pretty well. The OBS error starts out at 3 in the stratosphere, and near the tropopause, it reduces to 1.5, and then it increases gradually toward the surface of the Earth. And this is actually the settings that are found in a GSI fix file. So they have hardwired numbers in these ranges. And actually theirs is in every 50 millibar increments, and we made it so that you can just change the values in any way you want, go up, go down, and just put in the points on your little graph. It's pretty simple. There are many OBS functions actually, and a good number of them are for the satellite data. That's the most worked on piece of observation type so far. So this is just a list from the read the docs. The link is there. Hopefully you can go there and look at it. There's also how to create a new observation operator, which is actually, at times it can be challenging. I've done a few of those that are in this current release of JEDI. So starting with raw observations, we can prep for the DA, which is doing things like rejecting the clearly out of range data. And I just say an example, -90 Celsius to +60 Celsius, reject anything out of that range. And I won't read through all these on this slide, but basically you do generally tend to do a sort of workflow looking like this, where you do multiple checks. This was covered nicely in Fabio's talk with a flow chart. And then my caution at the bottom comes out of this, is something I put in because this has gotten me in trouble. I was expecting the filters were run sequentially by the YAML order, the order presented in the YAML. They are not. They don't have to be. Sometimes they are. And in the future, a hierarchy or dependence of filter B running after filter A, for an example, is definitely in the plans right now, and it needs to happen pretty soon. So this was yesterday's example, and I just have I think I have 2 more slides here, I hope, before switching gears. This is the SatWinds example. Bounds check, let's just make a sanity check of a -135 to a +135 meters per second. And not only are you checking on the individual wind components, you're checking on the velocity using an OBS function. So it'll do the velocity calculation to make sure that the velocity is also under 135. If not, reject the observation. Assignment of the OBS error, I went over this with air temperature as an example, but you can see how this one's a bit more complex, starting out with a 1.4 meter per second OBS error assignment above or below 1,000 millibars. And if you remember from the other slide of this X vals was in the opposite direction. It was top down. This is bottom up in pressure. So it does have this nice flexibility. You don't have to have it in one order or the other. The only thing you can't do is repeat of number. You couldn't say 800 millibars twice. It's illogical to do that. And anything greater than 1,000 millibars would be holding the constant value seen in the error value. So it would be 1.4 for all pressures greater than 1,000 millibars, and it would be 2.1 on the right side of the vector for all pressures higher in altitude than 100 millibars. The tropopause estimate, I mentioned this, so we're just rejecting all winds in which the tropopause, the observed air pressure of like a satellite wind is more than 25 millibars, 20 hectopascals, less than or higher up than where the tropopause is supposed to be. I mentioned that already. Eastward wind and northward wind get rejected when checking the wind direction angle. I mentioned that. So this is what it looks like in YAML. It's nice and short and really works very well. So with that, I'm going to need to switch to Wei Han to present.
Okay. Thanks, Greg, for a very nice presentation for the general QC and also for conventional. I think for my presentation is mainly focused on for the readings. The mainly two parts. One is about the bias correction, and also from yesterday we have some practical lessons to just remove some predictors to see the effect. Actually, for the satellite reading backtracking is very important, and also currently is the predictors and also the coefficients is mainly based on the statistical. So here is mainly what the bias correction looks like. Here's a constant term and also some predictors and with coefficients. These were predictors for different NW center. Actually, is using different predictors. For example, European Center and NCEP, using the different predictors. Here is an example for the European Center's predictors. And in the UI4 currently we read the coefficients and calculate the predictors and then sum them up to do the bias correction. And also here for the satellite reading bias correction is also I think is an ongoing topic, because we currently assume that the background is unbiased. So it's for some cases it's not true. For example, for some in the street atmosphere, we know there is some mode bias, so that will cause some problems. Here is what it looks in the bias correction in UI4. Here I listed the predictors is in UI4 source code, UI4 predictors. So you can see from the name of the functions, you can also guess what the predictors is. And one get the predictors, and here is in the Obs bias operator .cc, we can get compute the sum of the predictor contribution. Here is for each channel, for each predictor, and then we then it here it y bias is sum all the predictors up. So this is the implementation of the bias correction currently in UI4. Because currently the update of these coefficients is in the JEDI analysis framework. Here I mainly focus on the how we get this bias correction. I will show example for the bias correction using SMS as an example. Yesterday in the practical session, we have do some exercise. Just remove the orbital node dependent predictors to see the ascending and the descending the biases. Because for the SMS is early morning in the early morning orbit, so the antenna one side is day, one side is night. So one is in the descending and ascending node, so it's different. Actually, this effect should be removed during calibration of the sensor design. But unfortunately, for the SMS, there is some solar intrusion problems. So it's currently we're using these channels in UI4 to follow implementation in GSI channel 5, 6, 7, and 24. So it's the weighting function, the height is quite similar to some high peaking channel of MSOA. And here is a bias correction of MSS. Before bias correction, we just selected this channel, channel 24. Before bias correction, this is the O minus B. So you can find very clearly the ascending and descending bias differences, and also find the scan position dependence. For SMS, it's a conical scan. Actually, the local genial angle is the same, but during for different scan positions, they really some different biases. So these biases should be removed by bias correction before the observation. And here is predictors, cloud lake water, and this is done by Greg Thompson, and for the this is from Obs function. It's not and also we found that the cosine of latitude and the cosine of latitude is these two predictors are mainly for the ascending and descending node dependent biases, and also emissivity, scan position dependence, and lapse rate. So after bias correction, you will see here is the more uniform. The main departures is should reflect the model model error. So we could use this data to correct the model error to do the summation. And so yesterday, I'm not sure whether all the people have done this one. If you have any questions, please send me email or let me know. And also this predictor is from the cloudlakewater.cc. It's using this Obs function. The next one, I will show some examples for the severity QC. First, if somebody is very familiar with the GSI, here is what it looks like for the severity QC in GSI is a QC mode .apnante. So it's if on over sea, over land, or other surfaces, and also the about the terrain height. So there is what it looks in GSI. And also the background check if the absolute departure the greater than 2K. So it works, but it's not very easy for the people who is not very familiar with the GSI. And if you want to improve the QC for severity, you need to understand the GSI quite well. But currently, I think the UFO, the JEDI UFO, gave us some chance to, if you just focus on the what you are really your expertise. So what is in the UFO, for the QC, severity QC. Here the first tab in GSI surface check. We could blacklist some channels. Only use some channel over water, over ocean, open water, look like this. And for the terrain height, here is using domain check. If the surface the terrain height is only less than 1,000 meters, and also the background check using the absolute the background check absolute value to 2K. So I think it's more clear, and also it's very easy to implementation. If you have could do some contribution to the JEDI framework, just revise these YAML files, then it works. You didn't need to know all the data submission part. So I think it's really a very good opportunity for people who has some expertise on some specific area. And here is a result. Currently, we could replication GSI the readings for most of the sensors. Here example showing for the severity. D2 channel 5 and channel 6, which is 2 watt vapor sounding channels. It's the after QC, the opportunity number for these channels are exactly the same with GSI. And the omega departures, and also with very small differences, mainly due to the precision or some machine dependence. So I think it's very now we have a very solid basis, because we could fully replication operational QC. Then you could do some work for some improvement, and just focus on the sense and your area. And also here I would like to add a QC for the severity, and also in yesterday practical session we have. I'm not sure whether all the people have done this before, because for the geostationary satellite, here is the local gene angle, very large gene angle, so there is a very slant path. So we always you only constrain the local linear angle for the geostationary satellite. And here is the example yesterday practical session. To do that, just using the domain check and using the where function and specify the sensor local linear angle as well as the threshold. So also I think it's very nice to do further studies. If you want to perform some experiments, just change the YAML for some threshold, and then you can run your experiment and see clear what is the impact. And also for the UFO QC flags, there is the UFO filter QC flags.h has this specify which is the QC flags reflect to different the QC steps. And here I also show for the MSOA, we also have the fully replication of GSI capability. And here you maybe see this is the mean and the bias correction, and the green is without bias correction, and here is with bias correction. Maybe if you are familiar with radiance, you could wonder why after bias correction the omega B is even bigger. So I think it is still an open question. So then a very brief summary, and I think Greg gave a very nice condition on the QC filters and also for conventional. Here I'm mainly focused on the best correction and the QC for readings. I think through the exercises is a very good way to get some flavor of the UFO and to see if you change something to see the impact. And also for the path forward, I think still the software need to be refined, and also the science behind the software, and also maybe lots of people could make a contribution.